Okay, well, the school just gave me a brand new iPad, and it has this great program, and I also have another one that I'm working with together. And so instead of me writing out on a bunch of paper, I'm going to do this paperless and see if this works. So any feedback you want to give would be great. This is video 7, part 1 for Thursday the 10th. So this is meant to be viewed on the 10th. And yeah, we're going to talk about the TMB frame. So I'm going to start with just some background here. This is the Z plane, and there's Y, and there's X. I'm going to use some colors here. Here's my curve. It's going to come out like this, and then come up like this, and circle around like that. So here, this is my curve C, and C is parameterized. Let me go back to my black here. C is parameterized by some position vector RT. Okay. So what do? We pick a point over here, some nice spot in the thing here. We'll call this point P. Now coming off of this, of course, is our cap T, our tangent vector, which we know how to compute. And I'll put that over here. So cap T, it's supposed to be in black. Hold on. Cap T is equal to dr ds. Great. All right. So back to red here, and then so we've also now defined coming off this way inside. So in the concave direction, we have our normal vector n. And this vector is defined to be 1 over kappa, which is the curvature, times dt ds, right? Like that. Okay, and today we're going to define a new vector. So, and these guys are orthogonal. And so today we're going to, so now we've got, so as this point moves around the curve here, t is going this way and n's going that way, and it's moving. And so there's also a third direction of motion. And we're going to define this to be the cross product of t and n, which makes us go this way. Oops, it's supposed to be red. Makes us go this way. And B is, let's use a cool color here, yellow. So B is orthogonal to T, and it's also orthogonal to N. And it's the cross product of the two, and that's because we're using the right-hand rule here. Okay. Oops. Make that black again. There we go. Okay, so definition. The binomial vector, binomial vector. Oh, watch this. I think you can erase. Oh, yeah. Make it nice and pretty. Okay, the binomial vector of a curve in space is defined to be the cross product of the tangent, the unit tangent, and the normal. Oops. The binomial vector of a curve in space is defined to be the cross product of t and n, which is a unit vector orthogonal to both t and n. Okay? And let's get a handle on this thing, because we want to see how we can compute it. And this will be awesome. All right, here we go. Oops, where are my colors? Come back. So we're gonna let v, which is the derivative of r, and this is gonna be dr ds times ds dt by the chain rule. And dr ds above we showed is t. So this is t times ds dt, okay? So we're going to differentiate again here. And when you do that, you get the acceleration vector, which is dv dt. Follow along closely here. Now I'm going to take the derivative with respect to t of dr dt, which from the right-hand side here is this times that. Okay? And so now we're taking the derivative with respect to t of a product. So we get so let's see here. So I'm going to fix t and take the derivative of this. So I take the second derivative times t plus ds dt times dt dt. Okay? And that becomes, rewriting the first term, I have d squared s dt squared t plus ds dt of dt ds times ds dt. I'm going to pause a second here because what I did there is I took this guy and I did the chain rule on it. Right. Okay, just keep going here. Oops, I went black, sorry. So now I have d squared s, so the second derivative of f with respect to t, times t plus ds dt, and dt ds is kappa times n. Right, so if we go back up here, this is the part I like. If you solve this for dt ds, I'll highlight it. If you solve this for dt ds, you get dt ds equals n times kappa. And all I did here is I took dt ds and showed that it was kappa times n. All right, now rewriting this whole thing, we have d squared s dt squared t plus kappa ds dt squared times n. And remember, we're looking at acceleration here. Okay. So what we do here is we let a sub little t, a sub little big T equal d squared s dt squared, which is the derivative with respect to t of the norm of v. Hold on, let me erase that here. And that's by the definition of the function s sub t. And then we're going to let a sub cap n be kappa times the norm of v squared. And let's see here, I'm going to use some red here, okay? So this guy becomes, where's my red? There it is. This guy we're going to define to be a of t. And this guy we're going to be defined to be this thing. So we can write the acceleration. We can write the acceleration as this, well, the scalar a sub t cap t plus a sub little n cap n, where the formulas for a of cap t and a of cap n are right here and here. Okay. And these are called, some note, a sub t and a sub n are the tangential and normal scalars of acceleration. So these are scalars. Okay. So and this is key. Acceleration always lies in the plane that's formed with the vectors t and n, which is called the osculatory plane. Osculatory plane. Okay, so if I scroll back up to this original picture, I'll use this cool color. Oh, I got a whole bunch to choose from here. It's red. If I think of T and N, well, I don't think of it. T and N lie on a plane. And this plane, let's get a better color here. I'll put it in blue. This plane lies along there. So it's the plane through T and N. So all acceleration happens sideways. And if you've ever seen a plane fly, it'll do that. When you accelerate it, sort of goes sideways. It doesn't go up. All right, here's a formula, here's a formula for a sub cap n, and it happens to be the norm of a squared minus the scalar squared. Okay. All right, so apparently if you take any acceleration vector, you can write it as, so if you take any acceleration vector, you can write it as a sub tt plus a sub n, basically linear combinations of the vector t and the vector n. So that means we stay completely in the plane. So if here's the vector t, and here's the vector n, the plane that it creates, all the acceleration happens in there. Okay, so I'm going to stop here. See what this video looks and sounds like, and then I'm going to throw in some GeoGebra there to give you a picture of what happens as the T and B frame moves along the curve, and then make a second video and start talking about torsion. Okay, so this is the big example I want to do to go along with this TMB frame. And so we've got to do a whole bunch of calculations here. So let's just get into it. So we want to find T, N, B, and kappa for this helix. And then I'm going to throw this into GeoGebra, and we'll take a look at the animation of what goes on with these TNB vectors in kappa. So, all right, let's do this. V is the vector. It better not be my car. Minus sine Ti plus cosine Tj plus k. So the norm of V is going to be the square root of sine squared T plus cosine squared T plus 1 squared, and that's the square root of 2. So let's get all this stuff straight here. There's that, and there's that. So now T, which is V over the norm of V, is going to be, I'm going to write it like this: 1 over the square root of 2 times V, which is minus sine Ti plus cosine Tj plus k. So there's T. All right, so for N we need dt. And this 1 over root 2 just sits out front here. And the derivative of sine is cosine, so I have minus cosine Ti. The derivative of cosine is minus sine, so minus sine T j. Okay, and there's dt. So we also need the norm of this guy, or the length I should say. That's going to be 1 over root 2 squared, which is a half, times cosine squared T plus sine squared T, which is equal to 1 over root 2. This cosine squared plus sine squared is 1. Okay, so if we put dt over its length, we get N. And the 1 over root 2's cancel, so N becomes minus cosine Ti minus sine Tj. Okay. So we found T, we found N, now we went B. It's supposed to be in black, so B, oops, what just happened? Now we want B, which is T cross N, which is, let's see here, I, J, K. Now we're going to do the determinant. T is how do I want to do this? I'm going to go here. I'll just do it right. I is minus. Oh, come on. Why does it do that? minus 1 over root 2 sine t. J is 1 over root 2 cosine t. And k is 1 over root 2. T, there's t. And then n is minus cosine t minus sine t is 0. Okay, that's a vector k. So I want to expand across column 3 here because it's only 2 matrices instead of 3. So I take the vector k and then I multiply it by the submatrix minus 1 over root 2 sine t, 1 over root 2 cosine t, minus cosine t minus sine t, minus 1 over root 2 times I, j, minus cosine t minus sine t. Those are all vectors. Okay. So we get the vector k, which is, and the determinant is 1 over root 2 sine squared t minus a minus, so plus 1 over root 2 cosine squared t minus 1 over root 2 times minus sine ti plus cos tj. Okay. It's like an Energizer bunny problem here. So sine squared plus cosine squared is 1, so this becomes 1 over root 2 plus 1 over root 2 sine ti minus 1 over root 2 cosine tj. I'm going to rewrite this in order. This is 1 over root 2 sine ti minus cosine tj plus k. And that's our B vector. So it has a k component. And when we look at the video here in a second, so the B is going to have it's going to be going up because it's got a k component. Whereas the n component here, this sits parallel to the xy plane. So it's parallel to the xy plane. And you'll see that in the little animation. And then t it's got a k component, so it's always going to have a little bit of lift. All right, so let's look at this video and see if we can link all this stuff. All right, so my video was kind of cool. Well, what I wanted you to notice was that it looks like kappa doesn't change. You got to remember the helix is rotating around a cylinder. So it looks like the curvature is a constant. So let's show that. So kappa is 1 over the norm of V times the length of dt. And we showed before that the length of V is 1 over root 2. And we showed that the length of dt is 1 over root 2. And so the kappa is actually fixed. I thought that was going to highlight, but it didn't. Oops. And so the curvature is constant. And if you notice, the B vector had a K component, so it was sticking straight up the whole time. All right, part 2, which I'll make in a separate video, is about torsion, which is given, of course, another Greek symbol, tau. And we'll discuss that in the next video.